Greetings, calculus students. This is Mr. Myring coming to you once again digitally with a short video on the fundamental theorem of calculus, part 2. And so we've talked about the fundamental theorem of calculus already. Today what we're going to do is apply this to different sorts of problems, a couple different examples of where you have to apply the derivative and the integral in the same example. And so again, the fundamental theorem of calculus, if you not remember, has two different main parts. One of them, it just defines the relationship between the antiderivative and your original function, and then what happens when you have the definite integral, you're just plugging those limits of integration into the antiderivative. And so this particular example, or part 2 at least, will really focus on this definite integral part, but a shortcut to it because of the fact that we're doing both things. The big part of the FTC is that it tells us that the derivative and the integral are really inverse operations. And so a quick example, a couple of them here, we have find g prime, so find the derivative if the original g is equal to the definite integral from 3 to x of sine of t plus 1. And so you have a definite integral written here, so you have a function written as a definite integral. Lots of things you can do with that, but what we're actually asked to do is find the derivative of it. So that applies this inverse process concept very easily, very quickly to say we're asked to find the derivative of an integral. Since those are inverses, it's very easy to do. Our notes, if you look at the notes, it shows us that it doesn't matter what this constant is down here. Technically what you would do is you would do the antiderivative, which you could do. You would plug in x, you would plug in 3. That would be how you evaluate the definite integral part of it. But then you're just going to turn around and then derive that anyway. And so what the notes say is that you can jump straight to finding that derivative g prime of x and saying, well, x is going to go in for t, so you have sine of x plus 1 instead. And then what happens when you plug 3 in, it doesn't matter because that's going to go away and is a constant. The derivative of x is 1, and so your answer is just sine of x plus 1. X goes into where t is, and then you're done. So if I look at a second example, how does that change slightly? And more importantly, this is the application you'll be kind of doing. What happens when you have a function up here of x instead of just x? Something else going on instead of just that independent variable. So a similar concept here. You have a definite integral from -4 to sine. Slightly different notation, but it means the same thing. You're asked to do the derivative of this integral. And so you have this definite integral from -4 to sine of x, natural log of t minus 8 dt, telling you what your variable is. And so very quickly what you can do in order to evaluate this derivative and the integral is you can plug sine of x in for t. So you have the natural log of sine of x minus 8 in parentheses. What happens when you plug in -4 doesn't matter because the derivative is going to cancel out that constant. And then what you have to finish with is worrying about how to handle this sine of x and to derive that as well. So you would multiply by the derivative, which is cosine of x. So you would do that every single time when you are working through a fundamental theorem of calculus, part 2 problem. So in general then, if g of x equals the definite integral, or is written as the definite integral from any constant to any function of x, and you are integrating any function of t. So here's what you're integrating, going from any constant to some function of x, just like we had sine of x up there. Then that means the derivative, g prime of x, is going to equal this function just with h of x instead, so you actually do that substitution. So that's f of h of x. But then you have to multiply by the derivative of h of x. So h prime of x would be your final answer for that. So in general, this is how you handle any fundamental theorem of calculus part 2 problem. Thanks.